In this video, we are going to learn on how to calculate the pH of the buffer solution after the addition of small amount of strong acid or strong base. So we have two scenarios. The first one is the addition of the small amount of strong acid or strong base does not change the volume of solution. For example, here, the question asks you to calculate the pH of 25 ml of buffer solution, 0.1 molar CH3NH2 and 0.2 molar CH3NH3Cl. The Kb of the base is given. So our salt fully dissociates into CH3NH3 plus ion and Cl minus ion, and our weak base dissociates slightly into CH3NH3 plus and OH minus ion. Since we have a weak base and salt that form the same conjugate acid, this solution is a basic buffer solution. By using the Henderson-Hasselbalch equation for the basic buffer solution, we could find the value of the pOH. So substitute the value, we will get the pOH 3.66. So remember, the concentration of our conjugate acid is equals to the concentration of our salt. And then use the formula pH equals to 14 minus pOH. You will get the pH of the solution, which is 10.34. Next, what would happen to the pH after we add 0.0001 moles of strong acid into it? When we add a small amount of acid into the buffer solution, a basic species will neutralize it. In this case, our basic species is a weak base, which is CH3NH2. So when a small amount of acid is added, the weak base will neutralize it. So the neutralization reaction of our weak base with the strong acid is written as CH3NH2 plus H3O plus produce CH3NH3 plus water. Construct the reaction table by using number of moles. So we have mole initial, mole change, and mole final. So the initial moles of our base here is concentration times the volume of the solution. We have 2.5 times 10 to the power of minus 3 moles, and our strong acid is 0.0001 moles. So between these two, since the ratio is 1-to-1 ratio, the strong acid will become our limiting reactant, which will be completely consumed in this reaction. So the change in number of mole here is the number of moles of the limiting reactant. So our reactants will decrease in 0.0001 moles. Same goes to our strong acid, and our product will increase in 0.0001 moles. So the final number of moles, since this is liquid, just ignore the number of moles of water here. So the final concentration is the final number of moles divided by the volume of the solution. And then find the pOH of the solution by using the Henderson-Hasselbalch equation. So again, negative log Kb plus log concentration of our conjugate acid divided by concentration of weak base. So we will get 3.68, and then find the pH of the solution, which is 14 minus 3.68. So now the pH of the solution will become 10.32. And we can see that the difference in pH is 0.02. Thus, pH is not much affected. This is because when the concentration of the conjugate acid is increases, the equilibrium position will shift to the left and increase the concentration of the weak base. That's why pH is not much affected. When the 0.0001 moles of strong base is added, a conjugate acid will neutralize it. Construct the reaction table by using the number of mole. So we have number of mole initial, number of mole change, and number of mole final. So same like before, the change in number of mole is the limiting reactant. So the number of mole of hydroxide ion is less than the number of mole of our conjugate acid. So hydroxide ion is our limiting reactant. So conjugate acid will decrease in 0.0001. Same goes to the hydroxide ion. and the product here will increase in 0.0001 moles. So the final number of mole is 4.9 times 10 to the power of minus 3 moles of conjugate acid and 2.6 times 10 to the power of minus 3 moles of our base. And calculate the final concentration of each species and use the Henderson-Hasselbalch equation to find the pOH, find the pH, and calculate the difference in pH, which is the pH after addition of base minus the pH before addition of base. We can see that the pH is not much affected. This is because since the dissociation of a weak base is very small, pH is not much affected, even there is an increase in concentration of the weak base. The second scenario is the addition of small amount of strong acid or strong base into the buffer solution that will change the volume of solution. So let's have a look at the example. The question asks you to calculate the pH of 50 ml of buffer solution, which is 2.50 molar in C2H3O2H and 2 molars in C2H3O2Na. So the Ka for the acid is given. Since we have a weak acid and salt that form the same conjugate base, the solution is an acidic buffer. Use the Henderson-Hasselbalch equation to find the pH of the solution. So the pH of solution before the addition of strong acid or strong base is 4.65. When 50 ml of 0.01 molar of HCl is added, conjugate base will neutralize it. Construct the reaction table by using the number of mole. Change in number of mole depends on our limiting reactant, which is 1.5 times 10 to the power of minus 4. Find the final concentration. The total volume for our solution now will become 65 ml because we add 50 ml of the strong acid. And calculate the pH of the solution after the addition of the strong acid. We can see that the pH is not much affected. This is because the dissociation of the weak acid is very small. Even the concentration of the weak acid increases. When 20 ml of 0.01 molar sodium hydroxide, which is a strong base, is added, a weak acid will neutralize it. Construct the reaction table and find the concentration final. So our final volume is 0.07 because 50 ml of the buffer solution plus with 20 ml of the strong base added. So calculate the pH by using the Henderson-Hasselbalch. So this is the pH after the addition of the strong base. We can see that the change in pH is 0. So pH is not affected. This is because when the concentration of the conjugate base increases, according to the Le Chatelier's principle, the equilibrium position will shift to the left and increase the concentration of the weak acid.